Hi, my name is Maxwell Kreitman, and I'll be presenting some findings from a research project that was developed from the collaboration of Google DeepMind and the University of British Columbia on a model they built together called Genie, which is a generative interactive environments model. Our agenda today is an introduction, some model features, we'll talk about some model results, and AI implications. So this model in particular, its purpose is to generate interactive environments from various prompts such as text, image, and sketches, meaning hand-drawn pictures. It seeks to create controllable world and virtual worlds without labeled data or domain-specific requirements, also to enable users to interact and explore these environments on an incremental video frame basis, and it seeks to serve as a foundational world model for training generalist agents, especially in unseen reinforcement learning environments. Some of the model features include that it is considered a foundational world model with 11 billion parameters. This model was trained on 6.8 million 16-second video clips, again, totaling 30,000 hours in total of 2D platformer gameplay. This is styles of games such as Sonic or Super Mario, some of those classic games. Three key components of Genie include a latent action model, video tokenizer, and a dynamics model that will go into depth. Here's an overview of how the Genie model training began. It started with taking T-frames of video as input. There's one process of tokenizing them into discrete tokens with this component called the video tokenizer. Also inferring latent actions between each frame with the latent action model, and then the information from both of these is passed to the dynamics model to generate predictions for the next frames in an iterative manner. So to talk about the components, we also have to talk about kind of the architecture behind them, including this spatiotemporal transformer architecture, which is takes design cues from vision transformer. And the reason why the researchers didn't use a classical vision transformer is because they realized the computational requirements and memory requirements were quite high, which contained up to a big O of 10 to the fourth tokens for video processing. So they developed this architecture to balance small capacity with the computational constraints. So the way that this works is we have our input tokens, and then we have spatial temporal blocks, each containing this feed-forward layer, temporal attention layer, and a spatial attention layer. Each color represents a single self-attention map. The spatial layer focuses on different areas within a single time step, and considering each part of the grid separately. The temporal layer focuses on one specific element across all the time steps, treating each sequence of time points one by one. The latent action model has four kind of interesting pieces of information. Again, this is the component that learns from unsupervised, unlabeled video frames. It has 300 million parameters total with a patch size of 16, so a very small percentage of the overall parameters of the entire model. Again, it preserves that spatial temporal transformer architecture. And also the researchers limited the codebook, essentially the latent action possibilities, to 8 unique codes total. So on the far left, we have our, in this diagram, we have our input frames. The adjacent block beyond the dotted line represents the next adjacent frame. We have our encoder that analyzes this data, creates a latent action, and through the decoder process, it helps predict the possible next frame using the latent action defined. The video tokenizer, its purpose is to compress videos into discrete tokens, which helps with dimensionality and video generation issues. It uses a combination of a quantized variational autoencoder and also the spatiotemporal vision transformer that we described earlier. And it generates discrete representations for each frame. And here's a graphic to demonstrate, again, the video frames going through the encoder and creating the tokens, decoding the tokens, and creating the representations as its predicted output. The dynamics model takes both of those pieces of information and generates predictions for the following frame. It uses 16-bit floating point representation and normalization involving queries and keys. It performs 25 masked generative image transformer steps for sampling each frame at inference time. And again, it takes in video tokens and latent actions, embeddings, and predicts future masked video tokens. In this graphic, it's demonstrating how Genie works for action-controllable video generation at inference time, essentially when the model has been deployed. So on the far left, we have this block above x1 that represents an image that a player prompts. The image is tokenized using the video encoder, yielding Z1. The player has to specify discrete latent action by choosing an integer within the codebook. The dynamics model then takes the frame tokens and corresponding latent action and predicts next frame tokens in the Z2 block. And then the process is repeated in an auto-regressive manner, and tokens are decoded into video frames in X-hat2 simultaneously on the far right. Now we'll go into some of the model results. In this image, it's essentially showing the prompt frame and an adjacent frame after taking a latent action 4 consecutive times. So in each case, we can see character movement. On the top, the character kind of jumps off the platform in the top left from text to image. Again, on the far right, we can see the character is kind of in a red color, moving downwards from the platform. In the second row, we have a hand-drawn sketch as our prompt, and we can see that the soccer ball that looks like a pink soccer ball is moving up and to the right. Again, adjacent to that on the right-hand side, we can see a couple things moving in the frame. Both the purple character moves to the right, and then the heart also is kind of moving up and to the right. In the real-world photo example on the bottom left, the dog is moving to the left of the frame, and adjacently to that, there's a character with a red cape kind of jumping up and to the right. And again, the researchers really were confident that Genie had applications in reinforcement learning. So here's an example of creating generating trajectories in unseen reinforcement learning environments. So for player 1, we see the character kind of moving to the right and then jumping up. And then in player 2, it's just kind of scrolling to the right without the upward movement. We can see that the environment is pretty consistent between columns of imagery as well, of each slide. This slide is demonstrating that the Genie model scales very well with the addition of more model parameters, we can see that the training loss decreases with an increase in size overall. And also that the batch size, increasing the batch size leads to better model performance in addition. So what they used to evaluate the success of Genie in particular were two model metrics, including the Freitas video distance. And the way we interpret this is that it's the measuring the quality of the video generation, and the lower the value, the better performance, as well as controllability, which is peak signal to noise ratio, measuring the impact of latent actions on video generation. And we actually want a higher value, which indicates greater controllability from the latent actions. So in this slide, I included an image based on a different domain, essentially in the robotics domain, where each column is demonstrating a robotic arm movement from a particular prompt. And the resulting frames as we move to the right from each prompt shows the same latent action taken 5 times. So even without training with action labels, the same actions are consistent across varied prompt frames. And each of these additional columns have a semantic meaning down, up, and left. So we can see in the top case, the robotic arm is taking an item and putting it into the drawer and then returning. In the middle example, it's attempting to pick up a bag of chips, which is semi-malleable and not a very rigid object. And in the bottom, it's essentially returning an object from the drawer onto the table. So there were 3 main issues and areas for improvement identified by the researchers, including that Genie still has the potential to hallucinate some unrealistic futures. It's limited to 16 frames of memory, and it currently operates at 1 frame per second. So still has some room for improvement in terms of capability, but it's definitely on the right track. And for AI implications, we've demonstrated that Genie is very scalable, and with additional resources to create larger models with more parameters, and it has the potential to assist development of more powerful foundational models. It's effective to train, Genie is very flexible, and it can train effectively on video-only data, so it has the potential to work on many more types of internet videos. It also its generality suggests the possibility of simulating diverse, realistic, and other environments on a larger scale, and it hopes to, again, contribute to the development of foundational world models in the robotics domain. So that's it for my presentation. Thanks for viewing, and if you'd like to learn more about the paper, you can use the link that I've included on this page. Thanks.